All right. Welcome to United Astronomy Clubs of New Jersey. We're back here on site in Jenny Jump State Forest in Hope, New Jersey. So, welcome everyone who's joining here, and also welcome to everyone who's joining online. Now, because I see a couple cars still coming in trying to get settled parking, I'll give them a couple minutes to get down here. Welcome. If you're online joining us, do hit those like and subscribe buttons. It always helps us know we're doing a good job, and they're completely free actions. That being said, you can also check us out on our website, uacnj.org. It's where you're going to find a list of all our member clubs because we are a club made up of other clubs. Move your mic down just a little bit so you're not Darth Vadering the entire audience.
Oh, you can hear that?
Yes.
Can you hear that?
Luke, I am your father. Sorry. All right. Sorry, it just was distracting me just ever so slightly and derailed my train of thought. But you will find a list of our member clubs on our website. We do encourage people to join their local club because chances are the people who know how best to stargaze out near New York City are not going to have the tips they need for out here, and I'm out here not going to have the tips you need for out in New York City. So your local astronomy club, always an excellent choice. You can also check out our list of upcoming talks. We have one last talk that's going to be here in Jenny Jump for the 2024 season before we go online only during the winter, because unfortunately, oddly enough, when it gets winter in a state park, it gets icy and insurance is a little expensive at that point. So you can also check us out on our social media pages, our Facebook, our Instagram. We have a Discord channel, all great places to get in touch with us, ask questions, and share. People who have taken astrophotography always share images. I love to see them. With that, it looks like we have finally settled down out here, and most people have wandered down from their cars. So now it is the time for the safety briefing. It is unescapable. If you need to use the restroom, that is the porta potty in the back to my left, your right. It is illuminated bright red, so you can more easily find it in the dark. We also have a little museum and gift shop area. I will be manning that after the talk because unfortunately, as of yet, they still will not allow me to exist in two places at once. Once that happens, I will take over the world. But until then, I thank you for waiting patiently. In each of the little sheds out there, you see, it houses a telescope. The ones with the roofs rolled off, so the telescope can see the sky, will be open. We also have some observers with their personal rigs, so feel free to ask them what they are viewing. Always listen to their direction. And some might have visual telescopes, some might have their astrophotography rigs, so do be mindful. Ask them, hey, what you're viewing, and a lot of times they'll be happy to explain to you what's going on. In addition, when we are walking around, it is actually a pretty full moon night, so a little more light than we're used to dealing with. However, if you do need extra light, do try and keep that pointed towards the ground. We don't need to accidentally blind people. No weird flashlight raves. However, when we are going to leave, we are using our headlights. Because as much as we don't like getting blinded, we much more prefer getting blinded to getting run over. So let us avoid that amount of paperwork and hospital bills since we are in the U.S. With that, you're not here to listen to me blabber on. You're here for a fun science topic. And this topic is capturing the universe. And a whole lot of other words that I can't read up on that screen because it's far too bright. But giving this talk is Matt Cooper from NJIT. He, at one point, was an assistant research professor for the Department of Applied Physics Center for Solar Terrestrial Research. However, he has moved up in rank.
It was a horizontal. I'm a university lecturer now.
So,
I do more teaching I was supposed to be doing less research. That hasn't happened yet. We'll see if that ever happens. Probably not at this point.
Yeah, but he does many much fun science things,
Many much indeed.
and I unfortunately understood none of them when he tried to explain them to me. So maybe one of you will get a chance to figure out what I failed to. And with that, here's Matt.
Wow. Well, thank you for the introduction. Hopefully, after teaching 3 semesters of first year college students, I've gotten a little better at explaining. I apologize, Kim. Um, so this talk was inspired by a question I posed to my astronomy class. So it's an introductory astronomy class. It's supposed to be kind of a fun course you take in your spare time. And I asked my students whether or not we had ever taken a picture of the surface of another planet. What I mean by that is, have we ever taken a detailed picture? Like, can we see the mountains on a planet outside of our solar system? So, past everything that we have here, the nearest solar system, which is Alpha Centauri, have we taken a picture of one of those planets? Can we see details? Do we know if those planets have oceans? Do they have mountains? And a few of them immediately were just like, yeah, of course we have, duh. And I was like, oh, okay. Google it. So they got on Google, looked around for a second. Couldn't find anything. It was like, okay, go find a picture of Mars taken from the ground. Like, oh. So now there actually are some astrophotographers that are stacking, like, I saw one that stacked 22,000. It actually got pretty close to Hubble. Taking a picture of Mars from the surface just using standard like stuff that you'll find out here, they were able to do that. So we've gotten a little bit better, but even then, just how absurd is it to try to take a picture, to try to see something, the detail about a planet in another solar system? Because a question that I think everybody here comes up a lot, especially in the news and the media. The search for life. We haven't found life. We haven't found evidence of life. Maybe after this talk, I'll have given you a reason to think that maybe it's just because we haven't looked all that hard. So, of course, this was the question that started this whole ordeal, and the next thing you immediately have to ask is, okay, what are the capabilities necessary? Like, can we even make the lenses, the mirrors, the camera necessary to do that? Is that something that's within humanity's grasp right now? Like, have we made it that far? So, 3 things you absolutely must know in order to gauge whether or not that's something you can do are these 3 questions. So, we need to know how far it is. So nowadays, with our current worldview, we know that our sun is a star. It's another star, just like all the other stars in the sky. So we want to find the nearest one, and we need to know an actual number value for how far it is away. So that's the first one, and it's fairly difficult to accomplish. The second is what we would expect out of that solar system. Are its planets wildly different from our own? Is it like, can we expect there to be any similarity in the planets between what it has and what we have here in our solar system? Or is that a bridge too far? Like, are they just like completely different worlds that we would find even in the solar system next door? Yes. I'm not allowed to step over this line? Okay. I don't know if I can stop me as the problem, because when I'm talking, my legs are usually doing something much different. In a classroom, I have a board to keep me in place. And then the third is the brightness. So if you're trying to look at something, if it's not bright enough, it doesn't matter how hard you stare at it, you're not going to see it. You can stare really, really hard, but over time, it's just not going to be possible unless you have some very astoundingly accurate timekeeping equipment. So that first question, what is the distance? This is an old question, very old, possibly older than we have recorded history of. Again, we can't say anything about what happens before we have recorded history. In recorded history, the first person to really, or the first group to really start to add logic to astronomical observations, other than the standard the logics that have been applied before, telling the seasons through the constellations, using the summer solstice to know when your planting season should be. These are all things that have been done from antiquity. You have like stone circles where nomadic tribes even did that. But the Greeks really started to apply astronomy and logic together, and actually start getting numbers and starting to try to constrain what the universe was. Because at that point in time, I mean, their worldview, they had no flying machines for sure. There weren't aircraft going over. We didn't have satellites in space. All they had were their two eyes and what they could observe and reason and logic through. So here is just a smattering of different ones. So Aristotle, Eratosthenes, that center one there is Hipparchus, I always say her name wrong, Aglionis, and then Aristarchus of Samos up in the top right. I didn't break it. Oh. Oh. I'm trapped. Okay. I see. So, in order to understand the Greeks and understand what they were doing in astronomy and the successes that they had, you first have to understand what they thought the universe was. And in modern day, it may seem absolutely ridiculous that that was the view of how the universe was, but it was. And this wasn't something that was questioned. There were actual logical reasons behind all this. So the first is that the heavens are spherical. So when we talk about the celestial sphere, the Greeks actually thought that was a real thing, that there was a spherical shell out there in the sky, and that the stars were little jewels stuck in that. They weren't sure why the jewels were shining, but they were. Maybe they thought it was sunlight, but they're at some distance. If you went far enough out, you would find the celestial sphere. Okay? The Earth did not rotate. The Earth was stationary, immobile by number 6. So the Earth does not move in its place. This celestial sphere is what is rotating, and that's why the stars move. Okay? We know this to be true, clearly, obviously. The Earth couldn't move. The Earth is too big. The heavens must move. Logical. Okay, the Earth is the center. The Earth does not move. The Earth is not rotating around anything. So everything, the sun, the moon, the celestial sphere, the wanderers. Okay, so we have these odd wandering stars. They're stars, but they're different colors, and they move much faster compared to the other ones, and they go in different positions. So the wanderers are the gods. Mercury, Venus, Jupiter, Saturn, Mars. Those are something else. We know those aren't on the celestial sphere. So we know that the wanderers, the planets, they are moving in between the Earth, which is at the center, and the celestial sphere. So that is the view of the universe that a Grecian would have during their time. Okay, and number 5 is just saying that celestial sphere is a sphere and the Earth is at the center of it. It's not offset or anything. But not everyone thought this way. One particular Grecian that's near and dear to my heart is Aristarchus of Samos. Because Aristarchus of Samos, 1,500 years before Copernicus, suggested that the Earth may not be the center of everything. He suggested a heliocentric view of the universe. So 1,500 years before people were put under permanent house arrest for it, in Greece they were much more... I won't say accepting of it, but they did listen to Aristarchus' arguments. It wasn't just immediately like, no, that's silly, stop it. We know that the celestial sphere is out there, and we know the Earth has to be the center of it. The logic is sound. And the person that that disagreed with him most, I wouldn't say most fervently, but probably the most logically, was none other than Aristotle. So Aristotle shot down Aristarchus' suggestion that the sun was the center and that the Earth was moving around it. And it wasn't just like, oh, I'm Aristotle, haha, you're wrong, go on. No, it was not that. No, there was a sound logic and reason. So what Aristotle suggested was as a counter argument was that if the Earth were moving, you would be able to tell because the stars would move throughout the year. Okay, so if you were to look at the night sky on one side of the sun, and then you move, and then half a year later, we're on the other side of the sun, and you look at the same night sky, you should be able to tell the shift in the stars. It should be a large shift. This is what we know as parallax. But they didn't see the shift. The Greeks made computers to track the stars. Like, the Greeks were very, very good astronomers. They had fairly good timekeeping, like iron cog timekeeping instruments for their astronomic investigations. So they were no slouches, and they could tell that the stars weren't moving throughout the year. There was no parallax shift. Well, the celestial sphere can't be that far away. That's absurd. The universe is not that big. So I'm sorry, Aristarchus, you can't be correct. This can't be the case. The Earth must be sitting still because the stars do not change. And it would take another 1,500 years for that to get rewritten. So this is only going to work for the first few rows. I apologize. It's actually really hard to do this demo. So if you take your finger and put it up in front of you, full arm's length, and close one eye, and cover up one of these lines. You might want to, depending on what, if you pick your right eye, you might want to go further to the left eye, you might want to go further to the right. So hold it up and cover up a line, and then without moving your hand, open the other eye and close that eye. Do you notice that they shift? Okay, now change your eyes back, so go back to the original eye and move it closer. And then do the same thing. Notice how it shifts further as it comes closer to you. So this is parallax in essence. This is how we know the distances to some of the stars in the universe. This is how we measure. I think you can use parallax to get up to 40,000 light years. Okay, so parallax is pretty straightforward. What you just experienced there, so we have two cameras, our eyes. They are receiving light from one direction, and we are using a reference, in this case, our finger, to look back and forth. But in order to use it, you need a reference. So here we had the lines. That was our reference point to show us that, in fact, we were shifting back and forth. And this is what Aristotle wasn't seeing, and this is why Aristotle was so opposed to that idea, because the universe just could not be that big. It just did not seem reasonable. Well, nowadays we of course know that the universe was in fact that big. Aristotle was, although he probably had good reason, he was in fact quite wrong. So nowadays we can measure those distances using parallax. There are satellites that that is their sole job, is to measure parallax to very precise degrees of different stars. And in that time, we have found that our closest neighbor is Alpha Centauri. It's a trinary, which is quite strange to find, star system. Binary stars are pretty common. A trinary is fairly uncommon. A three-body star system being stable is not something you find super often. One of the stars is very small, so here you have the two main stars of Alpha Centauri, and then there's one very small one that doesn't usually appear. It's about 1,000 times dimmer. So our closest neighbor is 4.2465 light years away. So if you were getting a spaceship traveling at the speed of light, you still have a 4-year journey to get there. So, and that's our closest neighbor, and we've measured much, much, much further. We've measured out to 14.2 billion light years. So using various approaches and methods, we have been able to learn quite a bit about Alpha Centauri. We have confirmed that there are 3 planets orbiting Alpha Centauri. But wait, it sounded like I was going to say we haven't imaged, or we haven't taken a picture of the surface of a planet. We haven't. We have detected drops. So if we stare at a star's light, sometimes you'll detect drops in that star's intensity. So you watch it for months, and then all of a sudden you watch it for a month or two, the star's brightness is the same, then all of a sudden it drops a little bit, then it goes back up, maybe in half a day, maybe in a full day. And you can tell a decent amount of information from that. You can tell, you can find its orbital period, so you can tell how much mass it has. You can kind of make a guess about its radius, but this is all still inference. This is not us directly looking at it, okay? And the largest planet in that system is about 7 times the mass of the Earth, so that's not going to be all that much larger than the Earth. So it seems okay to reason that if we were to try to observe a planet around Alpha Centauri, we should be expecting to find something semi-Earth-like. It should be about the same size of the Earth, same brightness, so everything we know about the Earth and how much it shines, we can bring to bear here. Okay, so now the question is, what else is involved in that process? So we know what to expect. And this is what the Earth is going to look like from very far away. So that is the Earth here. This was taken by Juno. So here below the rings of Saturn, you see the Earth in the distance. That it looks like another star. So once you get far enough away, planets, stars, they have no difference. They are just points of light. Okay, so we are expecting this point of light in this other star system to shine about as brightly as the Earth is shining here, although unfortunately it is much, much, much further away. And therein, of course, lies the problem. As you get further away, things get progressively dimmer and dimmer. So I promise I'm not going to have a ton of definitions. I think this is my only slide, or maybe there's one more. Don't let me lie to you. So the 3 things we think about, or we talk about whenever we're talking about objects out there. So you can talk about from your your perspective, your point of view, what I need to do to receive the light that a particular celestial body is creating or reflecting. Or you can look at it from the celestial body's perspective. So how brightly is that celestial body shining? What is that celestial body's intrinsic brightness? How much does it itself shine? Maybe it's shining because its star is shining light on it, which is the usual case. Maybe it's a really hot world and it's got its own brightness. It makes its own light. So apparent brightness is what we see here. So when we talk about luminosity, you can think of that as the wattage that you would read off on a light bulb package. So that tells you how much power that light bulb is going to put out. The apparent brightness also involves how far you are away. So if you buy a bunch of bulbs that are the same brightness and you stack them up outward, you can tell how far away those light bulbs are. It would be great if the universe had a bunch of standard candles as well, and it actually turned out that it does. They're these very interesting blue stars. And then apparent magnitude, if you know about that, that is a scale designed to hurt feelings and sell chocolate. So I'm going to avoid that. Okay, so we want to know how bright this planet is going to be. Well, in order to do that, we can look at our own solar system, which we know almost infinitely more about. We can actually fly satellites to planets in our solar systems and observe things. So our sun's luminosity is a very large number, 3 times 10 to the 26. So 3 followed by 25 zeros. Okay, the Earth's luminosity is about 1 billion times dimmer, 1.6 billion to be precise. So if we put that in the magnitude scale, that's about a magnitude of 23. And magnitude is just a relative brightness thing. We can't use the normal scales 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That'd be great, but brightnesses vary a lot when you're talking about things in the sky. So unfortunately, there had to be another scale, and Hipparchus actually is the one that originally came up with the scale 2,000 years ago, and we're still using it with some corrections. Astronomy has a very old heritage. Okay, so now we have a relationship between the brightness of our sun and the brightness of the Earth. Well, we also know what the brightness of Alpha Centauri is. So now we can look at where on the scale would a planet around Alpha Centauri fall? Because for apparent magnitude, so what I have here is 23, we can observe to an apparent magnitude of about 35. Once you get much past that, 35 is the limit for James Webb. So that is the James Webb is observing the dimmest objects that humanity has ever observed, hands down. It's actually seen the furthest galaxy now. James Webb now holds that title again. Okay, so Alpha Centauri, to compare to our sun, so our sun has an apparent magnitude of negative 26. In apparent magnitude, the smaller you are, the brighter you are. So once you go to negative, you are getting very bright. So obviously the sun is going to be extremely bright. Alpha Centauri is negative 0.01. So if we have the same shift in the scale, that's going to put a planet around Alpha Centauri around 24, which is well within observable brightnesses. So the planet should be bright enough to see. Awesome. So it's not that it's far enough away that we just can't see that light. No, we should be able to get enough light from a planet around Alpha Centauri. So there's hope. I did not think that there was this much hope that we could see it. I honestly did not expect it to be bright enough. But as I said, we don't just want to see the light from it. So just seeing the light from it, we could probably do if we looked at the star long enough. It's going to be hard to do if the planet's in front of the star, which is usually when we are able to see them because we see that dip in intensity. But you're more seeing the lack of solar intensity, not the actual planet's intensity, because the planet's going to mostly reflect sunlight. So that's what you're really seeing. When you see a planet, you want to see it when it goes behind the star so that all that light is shining off the star, hitting the planet, and then coming to us. Okay? So whenever we study planets, we want to know, like, geological features. We want to know geological history. If you want to know geological history, you need to see the surface in some level of detail. You need to be able to see at least mountain ranges, right? You may not be able to see craters, and craters are a big source of information, but getting to that would be obviously insane. But what kind of camera would I need? So it's detectable, but how detectable? So how big of a mountain climb is this? So in astronomy, we divide the sky up by angles because we do consider a celestial sphere, although we absolutely know that that sphere is not a real thing now. It's just a coordinate system that we use. So we divide up the sky into degrees, both as the zenith, so going up, and then azimuthally. So you can look at the sky in kind of this grid-like pattern. You can use the constellations to lay these out as well, so you have good references. And when you talk about the size of objects, you can talk about them in terms of degrees. So instead of kilometers, now that object is that many degrees across, or taking up that much space in what we know as our field of view. So what we see. So our eyes actually give us a pretty wide field of view. We get about 110 degrees, which is really nice. So how many degrees is the moon across? So the moon's a pretty known feature in the night sky. It's pretty big. And it takes up about 0.5 degrees. Okay, so if you take 360 degrees all the way around, the moon is taking up half of one of those degrees. So it's not that big. I mean, it looks huge, but once you actually get the numbers, it's not taking up all that much space. So I'm going to compare the moon and how many degrees it takes up to our planet that is orbiting around Alpha Centauri. So Alpha Centauri, as I said, is 4.367 light years away, and that is an incredibly large number in kilometers. So assuming that whatever planet we're looking at has roughly the same radius as the Earth, it's going to take up about a billionth of a degree. That would be the equivalent of taking an image of the moon at a 1 centimeter resolution. which we can kind of do. It would be a whole lot of data, really big camera. I don't want to think of how much it would cost to build it, but we could do this. This is honestly not that insane. It would take a while, a long while, but getting the moon at a 1 centimeter resolution could be done with the proper equipment. It would be a money thing. But like I said, we don't just want to see the planet. We want to see the mountains. So we want to see down to 16 kilometers. That's reasonable. I think you could see a mountain range if you can get to a resolution of 16 kilometers. So for the last one, it was 1 centimeter. So let's keep that number. If we want to do mountains, if we want to see surface features, if we want to really dig into that planet and not just say, oh, hey, that planet's that color, that's cool, we're going to need to get down. That would be the equivalent of imaging the moon to 150 microns accuracy from the ground. So if you can imagine slicing up the moon into, I think that's roughly a trillion pieces. So slice the moon into a trillion pieces. One of those slices is what you're trying to be able to tell apart. So we do, is that feasible? I did not have the time to, unfortunately, I did not have the time to actually look at the numbers on the magnification. So the game that happens here now is a game of optics and cameras. So cameras have really, really tiny chips in them. We've gotten very good at how we do silicon. So those chips have pixels that are about 13 micrometers across, which is really small. So we can see really small things pretty easily. But that's really, 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 really small. So we're talking we would need pixels down to the nanometer if we were just looking at it directly. It might be possible to find an optic that could get that magnification. It would probably not be the cheapest thing to acquire, though. And this is all assuming that the light doesn't do anything weird on its way here, that nothing absorbs it, that it doesn't get knocked around by the intergalactic dust and goes away. So the universe is frighteningly big. Our own sun, we now with DKIST, we can actually see down to the 5-10 kilometer range. But that's still 5 to 10 kilometers. If you image the Earth at 5 to 10 kilometers, you'd have no idea that there was any life on it. It'd look green, but maybe the green's just part of the rock color. So in order to see life even on Earth, you need to see down to pretty good accuracy. You need to see down to, 100 meters, 50 meters, maybe 20. You can start to see buildings and stuff. Otherwise, you just kind of see gray and green splotches, which doesn't necessarily mean life if you don't know what you're looking for. So whenever people say that there has been no evidence of life found, this is true. And usually we're looking for signals from some advanced civilization, but just the idea of life in general, we're only about 200-300 years out from germ theory. So we just discovered a brand new form of, just, air quotes, discovered a brand new form of life here on Earth that we had no idea was here before. Maybe we just haven't looked all that hard yet. So if that causes you some anxiety, like, oh, are we alone in the universe? Like, we really don't know. And I really don't think we're at any stage to say that, oh, there is a scarcity of life, because it's really hard to look at the universe in detail. It takes a lot of effort, and even the closest star systems, we can't really tell anything about the planets yet. So there's still a lot of unknown to be discovered, and maybe we'll find life somewhere out there. Who knows? So thank you guys for listening. Anybody have any questions?
All right, thanks for talk. I'm gonna bring out the mic. So, for people here, basically you're gonna raise your hand. I'm gonna bring the mic to you so you can ask your question, and our online audience can hear the question. Online audience, you get the easy job of just typing. Oh, perfect. Mike, I know there were a couple hands over here. So.
How many solar systems are there?
How many solar systems are there? We don't know. There's billions. Every star has its own as far as we know. So,
Did you accidentally the entire mic?
we'll see. Okay, it's back for now. So yeah, every star, as far as we can tell, every star has its own planets.
Okay. Hey Chris, can you grab a battery? Okay, so he's gonna be grabbing a battery.
Thank you. Yeah. What's up? Can you say it again? I didn't hear you, man. No. Yeah.
Here's the mic back. New battery. How many solar systems are there in Andromeda galaxy? we're getting into questions he definitely doesn't know. Uh oh, right.
How could you know that?
All right, you want to go back in the area?
Yeah.
Put the speaker back in the jail cell. Okay.
Yeah, I'm stuck back up here.
So
past
our
this little line.
next online question is, who is your favorite astronomy figure?
Aristarchus of Samos. That's why he was in the talk. He's as
Hey, sometimes
undoubtedly
you
my
can have
favorite.
a non-appearing favorite. All right. Why that particular dude?
Because it just seemed like he kind of knew how things were going. Like he also figured out the distance to the sun and moon back in like 200 BCE. So that's pretty awesome. He got close. He thought the sun was about 20 times further away than the moon. Yeah.
All right, we got another question out here.
What's the biggest planet?
In our solar system,
Yeah.
Jupiter.
All right. And was there? Oh, perfect. I saw from the opposite corner.
So, do scientists have an idea of like how many years or decades it'll take before we develop the technology to be able to like observe Alpha Centauri at the granular or like the crater level?
Probably not. I'm not sure anyone's really thought about it all that much because it's such a difficult thing to do, and there are other complicating factors that make it even. What I've shown is not the big problem. Which sounds insane that the actual ridiculousness of the size is not the big problem. The big problem is what happens to light when it goes between the space between here and Alpha Centauri. Some of the wavelengths get absorbed, so we lose some of that information, especially in the visible. So there may be something else that's the reason why no one's really thought about it. But I'm not entirely sure. I mean, I think there's still enough unknowns with our own solar system that to try to push for something like this, because you wouldn't be able to do this on the ground. The atmosphere would completely toast any attempt to do this. You would have to go into space. So you're talking about a telescope going into space that its express purpose is to do this. So that would be a pretty big undertaking, I think.
All right, and an online question along that lines is, how long would it take to get to Alpha Centauri at the current top speed achievable?
Ooh, I actually don't know what our new top speed is.
What was the last one you knew?
New Horizons was boogieing pretty good. I think it was moving at over 100 kilometers. Um, I think that using our current tech, I think you're still looking at well over 100-year journey, and I don't think you satellites handle getting sped up to ridiculous speeds a lot easier than humans do. Um, as far as the tech to make something go that fast, I think you're looking at about 80 years. As far as the tech to get a human there, you're probably looking at 300 to get them there without pulping something important.
Yep, need all the important bits inside. All right, there's another question.
I know this is probably the same as the how many solar systems are there, but how many universes are there?
This lovely question. We don't know. We have no way of knowing. We
Knew
cannot
it,
step
knew it.
outside of our own. There are suggestions that there are other universes, particularly in quantum mechanics and particle theory. There are certain particles that, based on our current understanding, would suggest that there are other places outside of this particular place that they can go. But as far as where that place is, how that place is there a place an exact copy of our own? We can't. As for the moment, we are stuck here too. We can't step outside and see.
Currently, our universe is like our speaker. He cannot escape.
Yeah, trapped in the confines.
I did the solar system walk earlier today, and Jupiter was like huge star system. Go solar Saturn. And also, if Jupiter's an is egg shaped, so would Jupiter be a dwarf planet?
No,
Also, on Uranus, it follows all the planet.
He's wondering what qualifies a planet as a dwarf planet versus a planet.
Okay, yes. Why Pluto got kicked out? They didn't like Pluto. No, I'm kidding. So it turns out that there are actually several other planets like Pluto. So, it was either that we were gonna have to make Pluto not a planet, or we were gonna have like 15 or 16 planets. But the dwarf planets are very peculiar, and it's the reason why we don't consider them to be planets. So a planet, by definition nowadays, so the modern definition, a planet formed with the solar system. So the solar system started off, as far as we know, as this giant hot ball of material, and slowly over time that ball cooled down and it spun out. And as it spun out, you clumped up matter at different distances. That matter slowly cooled, pulled itself together, and made a planet. Most of those are in the ecliptic plane of the solar system, so they're all orbiting around in the same plane of the sun. The dwarf planets are not in that plane. The dwarf planets can be at moderately high above that plane or really high above that plane. So the dwarf planets are not native. The dwarf planets did not form here. They formed elsewhere, or maybe they formed out of a collision with something in here, but they did not get here the same way that what we consider a planet did. The dwarf planets got caught. So they were flying through the universe on their own, and they hit our solar system, and they just stayed.
All right, online people, if you have any questions, do get those in. I just like to give you guys a bit of a heads up, because by the time you hear this, we've moved on to the next two questions. All right, so I got two questions over here, and
How many galaxies are there?
Thank you. More than we can count so far.
How did Jupiter get its name?
how did Jupiter get
Ooh,
its name?
I actually do not know. I mean, it was named after the Roman god Jupiter. So Jupiter was one of the gods. So Jupiter, Venus, Mars.
The Greek analog would be Zeus.
Yeah.
So,
So I don't know where the word Jupiter comes from, though. Like, it's Roman, but I don't know what it means.
Yeah, no, I thought I knew, but now I do not. And I see another one back there. Like I said, anyone, if you have a question, do raise your hand.
So my friend had a question about the universe. So how old is our universe?
Our current estimate puts it around 14.4 billion years. 14.4-ish. I think 14.8 billion years. 13? The last estimate I saw said 14.8 because we've observed out to. So, with observing very long distances, you look back in time, and we've looked up to 14.2 billion light years out. So, if it was 13.8, we should have seen the edge by now.
Right. The question was, what was the weird gradient on the bottom of the picture of?
Oh, that down there. No, it was no. I don't. Juno never went near the atmosphere of Saturn. That would be a very bad decision. That could have been. That may be like something they added to the image after the fact. Like some of these images are doctored a bit. That could be. I mean, it's on the night side, so it could be that's where this. It could be that's.
If
Where-
it's looking along its own body and its own body is reflecting light too, so
No,
it could be a.
it's the spacecraft. You shouldn't see any albedo from the spacecraft. They usually try to control for that. It could be that that's the direction that the sun's in. Maybe there was a one of Saturn's moons was reflecting some sunlight over in that direction.
All right. Well, unfortunately, we don't know, and I do have someone who's been waiting for a question here.
Okay.
So.
It was mentioned before that there are moments when matter from other solar systems like escapes those orbits, right, and it could come into like our solar system, right, when we're talking about dwarf planets.
Right.
What information can we like get from those matters to infer about other solar systems?
Oh, quite a bit. So, if a dwarf planet formed in the disk, so that protostar, so as the protostar cools, that disk expands out. That's all this material from the same original clump. So, if a dwarf planet was from another solar system, if it was actually like one of the last clumps that formed on the very edge of the solar system, and its sun just couldn't hold it and it got thrown out, you still know a lot about the geologic history of that particular protostar. Like, you know what elements were making that up. You would find traces of the heavy elements, so like uranium, plutonium, some of the other ones like molybdenum. So based on what you could pull out of that planet, if you could get a sample of it, especially deep into the core of the planet, you would be able to tell a lot about kind of the history of that star. Did that star form after supernovas had already started? Was it a really old solar system? There's a lot of information that can be buried in those. If we were to land something on Pluto and take a soil sample, I think we would find a very different thing to what we usually see in the solid planets, or what we call the cratered worlds of our solar system.
All right, we got another question here.
Thanks. Hi. As far as observing planets that orbit other stars, how you said we're waiting for the star to go in front of, the planet to go in front of its star and dims a little bit. Are we always parallel to all these planets' arcs where they will pass in front of the sun, or are we ever on top of them where they will go all the way around their sun?
They are randomly oriented in all directions. So because we think that most solar systems form the same way, we do know that those planets are always going to orbit in the same plane of the star. That plane is, as far as we know, completely randomly oriented. So it is a shot in the dark. So it happened that with Alpha Centauri, the planets do move in front of it. But no, you are not guaranteed. Like your orbits that ecliptic plane could be completely flat compared to us, and we would never see any dimming. So yes, this is one of the risks.
All right. I thought I saw another person out here with their hand raised. All right.
What's your opinion about imaging the mega structures out there?
In regards to what's causing them,
No, like, do you believe? I've seen some journals showing mega structures around the sun, and they're imaging them somehow.
mega structures.
Not around our sun, but suns in distant galaxies.
I'm sorry. What?
Dyson spheres. That.
Yeah, mega structure is a new one for me. Like, is it a magnetic structure? Is it like a? Are they talking about like they think they've seen a Dyson sphere or something? A Dyson. Yeah, one man's Dyson sphere in a spectra is another man's planet. You have to do a lot to show that there's a structure that isn't naturally occurring, that is completely surrounding a star. And if it's completely surrounding the star, then why can we see the star? There's a lot that goes into that. I don't think we could unequivocally show that for even a star that's relatively close by. So I'm always quite skeptical when people say that they've seen mega structures. Like, what's the evidence in the spectra, and is there another explanation? Because if there's a species, if there is some type of being out there that's capable of building structures that big, they should be putting off emissions that we would detect. Like, they've been doing it. Obviously, they've been that advanced for a long time. Those emissions should be already have hit us by now. So that's kind of suspect. I have an opinion. Yes, I think that it's I think that if we find it, it can stand up to skepticism.
Yeah, that is one thing about observing anything. If you are observing something 100,000 light years away, you are observing something as it was 100,000 years ago. So, even if there is currently life on there or something that could produce a structure like that, there was not anything like that potentially at that time. Much like if someone looked at Earth from that far away, they'd still be seeing dinosaurs or some weird things like that. Maybe not even dinosaurs, maybe before dinosaurs. And they'd be like, yep, that's a molten hunk of rock. Right. And I see a couple. I'll get to you after I get through this one.
What is the brightest sun?
What is the brightest sun?
Yeah.
I actually did look at that today. It's about 1 billion times brighter than our sun. So we would not be able to look at it. If it was our sun, we wouldn't be able to look up. It would be really, 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 really bright. We'd probably have to live underground, actually. Probably would be fun. I'm glad we have our sun.
All right.
So, is New Horizons coming back? If so, it's probably back already because it's coming back 2024.
New Horizons isn't coming back, bud. Yeah, sorry. We send they keep going. They don't turn around.
That's on a one-way trip.
Yep.
All right. Were there any more last-minute questions? Okay. Let me.
It's actually going to catch Voyager eventually if they keep going.
Oh, just 1 minute. Let me get the microphone.
I think that kid earlier meant to say what was the brightest star observed in the sky.
Yeah, he did. The brightest sun. Stars are suns.
Do you know the name of that particular star?
No, it was
He
a set
probably
of. It
would have
was a
had I
series
not
of.
asked him.
This one was a series of numbers. It's a fairly new discovery. It's WASP-187, I think, capital WASP.
All right. And we got one more, and then we're going to start wrapping it up.
All right, so you mentioned that there are other mysteries in our own solar system that we should explore before imaging other planets. I was wondering, what are some of the top ones you think we should be exploring today?
Well, we don't know if Mars has subsurface water. That's a good one. We don't know anything hardly about Venus's surface at any resolution. We don't know what's in the ice on Europa, so Europa Clipper's great, but if that follow-on mission doesn't happen, I think we're missing a great opportunity. Uranus is actually quite interesting. We're still not sure what happened to Uranus, but it is spinning on its side. Something knocked it over, and that's really hard to do to a planet. So we don't know how that behaves. Its magnetic field's on its side, so its magnetosphere is probably the wildest thing any magnetospheric physicist has ever seen. There's a lot of really interesting things that we still don't fundamentally get about. I forget if it's on Chiron or Pluto, but there is a mountain inside of a cave. A whole mountain that is in a hole. We don't know how that happened. Just geologically, that doesn't fit. So there's still a ton of interesting things we can find in our own backyard, I think.
All right. So I want to thank you all for joining us. If you have any other questions, you can ask. Feel free to ask Matt after the fact. I do want to thank you all for joining us, not only here, but online on Twitch and YouTube as well. Don't forget to hit those like and subscribe buttons. For anyone who's still here, just remember, if we're using flashlights, do try and keep them pointed towards the ground. And when we do go to leave, please use your headlights. We don't need to accidentally run people over. If you need the... Wow, that's really bright. And I'm not even looking at that. If you do happen to need the restroom, that is the porta potty in the back. To my right, your left, and I will be in the little museum and gift shop area. With that, everyone have a great night. We do have a number of volunteers around willing to show you things with the sky. Have a good night, everyone. Clear skies and good seeing.